So what I wanted to do today, it's sort of a tradition that we have that I start this data summit by talking about our kind of evolving view of data, and also somehow doing a bunch of adventure demos that I've never done before. So I'll be doing that here. We'll see what fraction of them work. Well, this year actually, I think we have a very big story that's been kind of developing for close to 30 years now. And it's kind of made possible in many ways by a sort of deepening view of data. And it has to do with our Wolfram Language system that we've just started to bring out this year, and that, as I say, we've been working towards for a very, very long time. Both Mathematica and Wolfram Alpha have been essentially building blocks of what is now emerging as the Wolfram language. Let me just start off here. So, oops. So kind of the goal with the Wolfram language is to make sort of a new kind of computer language that is knowledge-based. Typical computer languages, the idea is the language consists of a small set of primitives, and perhaps people over the course of time build libraries for different kinds of things in that language, but the language is kept sort of as small and simple as possible and kind of just wraps around the fundamental operations of a computer. Our goal with the Wolfram language, and it's taken sort of 30 years to build towards this goal, is to do something, in a sense, much more ambitious, to do something which really takes advantage of all the knowledge that we now have, and to sort of have a knowledge-based language in which as much knowledge and automation is built into the language as possible. So kind of the idea is that directly within the language we have capabilities for all kinds of different things. The notion is that we should set it up so that we as humans sort of specify as little as possible, just sort of specify our goals in a simpler way as possible, and then it's up to the system to figure out automatically how to achieve those goals as well as it can. And also, in order to do that, we have to build in a lot of knowledge. Part of sort of that knowledge is algorithmic knowledge, all the various different kinds of algorithms and meta-algorithms to do all sorts of different kinds of things, and part of it is data. And as we built out this language, a crucial element is its interaction with the cloud. And in a sense, the very existence of this knowledge-based language is made possible by interaction with the cloud and by the fact that we can store terabytes of data in the cloud, curated and ready for the language to use. Well, Wolfram Alpha has been sort of a consumer way to present the knowledge that we've accumulated, and so let's just start up Wolfram Alpha here. Sort of the idea of Wolfram Alpha is, if it wakes up, oh, that's bad. I think I should sign in. I got to support our Pro version. So the idea is you ask it a question. It tries to give you a report of the answer. I suppose a good. This was a query that when Wolfram Alpha was first developed, this was a query I said would never work. But it turned out there is data on the number of goats in France and all kinds of other good things like that. I think we can ask it. Let's do this. Oh, that's a bad sign. Let's say we ask it about something which involves real-time data. This is sort of an interesting combination of a real-time feed of data and actual computation of celestial mechanics to figure out where this particular satellite will be. And if we go and scroll down, it'll tell us things that it computes based on where it thinks things that are relevant, like when will this rise from the place that it thinks my computer is in right now. So we've been steadily adding all sorts of different kinds of detailed data to the system. So we can ask it, how many Urdu speakers are there in the US, and hopefully it will respond and tell us that. Or if we can ask it something like, there's some results. Okay, it's about the same number of people as attended the Woodstock fair and so on. We could ask it something like, how many baseballs fit in a Boeing 747. And that requires some combination of kinds of knowledge, and gives us an answer of 4.8 million there. Or we could ask it, let's say we could ask it about let's try asking it about a hurricane. Which hopefully will, I didn't spell correctly, but anyway, again, this requires some feed of real-time data and then combining that in a variety of ways with actual computation now. Let's see if I can get one more thing to work here. Here we go. So let's for example, here's another kind of query. We can ask it about Van Gogh's Starry Night, and it should know something about that too, and it'll have an image, and it'll tell us all sorts of things about when it was painted relative to Van Gogh's life. I didn't know it was actually so late in his life. Okay, that's interesting. Or we can, the Wolfram Alpha gets used sort of every day by millions of people, lots of professionals, lots of students. For some of for the student folk, they're always a collection of popular culture things which they like a lot, and so it has data on many kinds of popular culture things. There's the distribution of weights and heights of a certain kind of Pokemon, if that's what you're interested in. Or for example, here it has a lot of data on kind of popular culture. So here, for instance, is oh, strange. Okay. I thought it was going to give me a word cloud for this popular song. Maybe I have the name of the song wrong. I'm not a big expert on these kinds of things, but it should give us a nice. See whether it's figuring out what to do. Oh, there we go. Okay. So, okay. It's not the okay, not the most exciting set of words there. So okay. This whole Wolfram Alpha effort, which Wolfram Alpha came out a little bit more than 5 years ago now, it's something that's been. There's both the consumer-facing version of Wolfram Alpha, which I'm showing you here, which is operating on public data. There's a pro version which operates on data that people upload, small amounts of data that people upload. There are custom versions that we've been building for a whole variety of organizations that make use of internal corporate data using the same technology stack. This has all been it's also, Wolfram Alpha has also been used in lots of other places, for example, in various intelligent assistants like Siri and so on. It's been a big effort acquiring a great deal of data, getting that data and making it computable. In a sense, the sort of first step with data is to get it so that it's in digital form and you can, in principle, get blobs of data. The next step is to set the data up so that if there's a question that can, in principle, be answered on the basis of that data, it's actually possible to automatically get the question answered. And that's a kind of much higher standard for the data, and that's a lot of the effort that goes into Wolfram Alpha is taking data from sort of digital form to computable form, injecting kind of the expert knowledge and the methods and models and calculations that are needed around the data to actually be able to answer questions on the basis of the data. Well, we developed all this stuff for Wolfram Alpha. We've got thousands of different domains of data, many terabytes of curated data, and so on. The exciting thing that we've been able to do now is to leverage all that effort in building this data into the Wolfram language. So it's let me kind of show you a little bit about the Wolfram language. Kind of the idea is, as I say, to have a language where as much knowledge as possible is built right into the language. So let's try and get started with some things here. So you can interact with the language. You type in a question, you get back an answer. If we type in, let's say we type something like this in, we get a plot. Or we could type in something slightly a little bit more elaborate. We'd get my all-time favorite science picture, or we could type in something like this, and now we would start getting a little user interface built. We have this manipulate that is now set up to provide a user interface that allows us to compute things. Well, the idea of the Wolfram language is to be very general, to be able to compute with any kind of data we're interested in. So, for example, if we want to, we can compute with, let's say, networks. I could pull in my kind of Facebook graph. It's pretty boring. This is a really good approximation to my Facebook graph, a random graph with some number of nodes. We can go ahead and take this graph, and now we can let's just pick up this graph here, and we can just go ahead and do computations on that graph. So, for example, here I worked out communities within that graph and so on. Or I could take, as well as dealing with networks, I could deal, for example, with images. Let's see what happens if I do this. Let's see. Okay, let's try it again. Okay. Lousy picture, but that's okay. So I could take that image, and I could just go ahead. Let me pick that image up here, and just go ahead and put that in here. And we can compute with this image. We can then, break it up into little pieces. We could, for example, let's try doing this here. Let's try. And we could maybe assemble that image again. And now we've got it assembled in little pieces. Let's try and run edge detection on that image. We get a result, and so on. So again, sort of a different type of data that the Wolfram language can deal with is image data. And we have sort of built into the Wolfram language kind of actually sort of the world's most complete at this point collection of kind of algorithms and meta-algorithms for image processing, all sort of directly built in a coherent way into the language. So these are things dealing with kind of abstract data. One of the big points of the Wolfram language is it also knows about real things in the world. So we can ask it, sunrise today or something like this. So we could say, let's ask it about planets. And what I'm doing here is I'm typing something in that's making use of the Wolfram Alpha natural language understanding stack. So I can just type in these little control equals things. I can just type standard natural language, and it will be interpreted into precise Wolfram language form. So here I can say, let's say, list of entities. Okay, there are a bunch of planets. I could say, for example, give me for the entity value associated with each of those entities of an image. So here I'll get images of planets, and maybe I can go and do some simple image thing with these. Let's say I just do an image collage. Maybe I could I could, for example, edge detect that, and so on. And I can go and so I can ask the system about lots of kinds of things. So let's say I type in G8 or something. It'll probably interpret that hopefully as group of countries. Okay. So let's say I say let's for example ask it to show me the flag entity for each of those countries. Okay, I have those flags. I could go ahead and I can do whatever I want here. I could do edge detection on those flags if I wanted to, all those kinds of things. Or for example, I could say, let's say I want to know the capital cities of those countries. Okay, there they are. Now notice that these things that I'm dealing with here, these are entities. So the Wolfram language is a symbolic language. So everything is represented in this very uniform way as kind of a symbolic expression. Some things that are represented as symbolic expressions are things like networks or images. Other kinds of things that are represented as symbolic expressions are things in the world, like cities or planets, those types of things. Well, so I could then take one of those cities, and I could go ahead and I could say, show me geographics of a geodisk 5 miles around the center of Washington, D.C. There's the result. And of course, we have mapping data for the Earth and so on in the system that we can compute with and so on. So a little bit more on the Wolfram language. Here's another thing. We've tried to make the system as automatic as possible. So for example, a big thing that we built in was lots of state-of-the-art machine learning algorithms, and you can just feed in data and say, for example, set up a classifier for this data, then we can take that classifier that's been built and apply it to a particular piece of input, and we get that result. Or let's try something, in a sense, it's a kind of form of curation that we have with machine learning. So let's take some data in. Let's pull in the plain text from the front page of the UN website, okay? And then let's go ahead and take that data and let's split it into one string per line. And then let's go ahead and say, and use a kind of a curated classifier that we've built, which classifies human languages. And we can go ahead and say, classify that into which human language each of those utterances is. And so long as they're long enough for it to be able to tell what's going on, it should be able to tell us what language they are. So this is, so these are kinds of things that are built into the Wolfram language. Another type of thing also sort of leverages this kind of concept of symbolic computation is we can do things like build reports. And for us, kind of the template for a report is just another symbolic expression. So we can go ahead and say, the time is, and then we can say, let's put in an expression here that says now, and then let's say, I don't know. So we're building up a report here. This report is just a symbolic expression. We go ahead and say, let's generate an actual output of this report. This is the template for a report where that, so now if we generate the output, it'll say the time is, and then it will fill in, for now, it will fill in the actual time. So this is just another piece of the whole picture of sort of everything as a symbolic expression. Well, so are the documents that we're dealing with, so are the templates for reports that we're producing, and so on. Okay, so one of the sort of the big ideas here is to sort of unify everything into this one knowledge-based language. Another big idea is to take that language and make sure that it can be sort of deployed everywhere. So what I was showing you here was the language just running directly on my computer. You can also use the language in the cloud. So for example, I can just go to the cloud here and I hope, yeah. And I could go just purely in a web browser, and I could do the exact same things that I was doing before. I can do my little computations and so on, and I could, for example, let's say I set up a plot here. I could do any of the computations that I was doing before. I can do now directly in the cloud, just in a web browser. And so now we're creating, we call the kind of computable documents that we're producing CDFs, the computable document format documents. This is now a cloud CDF where we're just operating directly in the cloud, but I can now interact with things. If I took that and I put it on the desktop, then you'd see the exact same thing happening, although now it doesn't have to go back and forth to a server. It can operate purely locally there. So it's so this sort of this complete interface is available in the cloud. You can do some very interesting kinds of deployments in the cloud. You can also take the same set of things and deploy them on mobile devices. And sort of the concept of the language is to support sort of all forms of computing from the very small to the very large. So you'll see the language running on giant supercomputers in a massively parallel form, and you'll also see the language running on tiny embedded processors that are kind of the size of one's thumb or something. There are many different places that the language can be deployed. The idea is also to do what I've shown you is kind of this interactive session that's a very convenient way to kind of explore and discover and create things with the language. But there's also a lot of deployment that one can do with the language. There are many forms of deployment. So for example, one thing we can do is, let's say we want to build a little web app. Let's build a form on the web. So this is going to say, create a form, and it's the web, so cats are popular, so let's make this something that involves cat breeds. So what I'm telling it to do, if it will let me sign in, oh, come now. Let's try that one more time. Okay. see if this works this time. Come on, think about it. Oh, there we go. Okay, so what this is doing is it's saying deploy to the cloud a form, and the form is going to have one field that's called breed, and that expects to be being given a cat breed. And then what it's going to do, the actual action that this little web app is going to do, is it's going to produce a picture of that cat breed. Okay, so let's try it. So now we have a form here that has this one field that asks for a breed, and this is what we call the smart field. It's a field that's making use of our natural language understanding stack to be able to let one just enter things in plain natural language. So we can say Siamese here. Let's submit that. We duly get a Siamese cat picture. Let's make this a little bit more complicated. Let's say let's make our form have two fields. Let's say one field is the cat breed, one field is an angle. And what we're going to do now, so let's try our Siamese cat again, and let's say at 60 degrees, and then what should happen is we should get the same thing, a picture of the cat at 60 degrees. Okay, so what we're seeing here is we're taking just Wolfram language code, and we're creating something that can be deployed on the web. So when we create that form, we can interact with it on the web. When we ask it to do a computation, it will go to our servers, do the computation, return the results to the web. And you can set that up in a very general way. So for example, here, I could also set up an API that's a cat breed API. So now I can go and I go to the web, and this will now be an API. Okay, I'll need to actually give it some input here. I say breed equals Siamese as it's a RESTful API, so I'm giving this on the URL line. And now I could have embedded that if I needed a cat breed picture inside my application. I could have embedded that anywhere in my application and called it from that application. Now this API is just a symbolic object like everything else, and we can take that symbolic object and manipulate it in various ways. For example, we can say, give me embed code that will have code for calling that API from inside an external Java program. I can do it for lots of different, sort of all the popular computer languages and so on. So what this will do is it will set things up so that if I put this code in my Java program, it will then call out to this piece of Wolfram language code in the cloud and do a computation with it. So it's and this is something. There's a kind of a complicated technology stack here, because in this case, I'm having this embed code call out to our cloud to get a computation done. You can call out to our public cloud. You can have a private cloud inside your infrastructure. You can also have a local version of the Wolfram engine that this exact same piece of code can be set up to call a local engine on your machine. Or alternatively, you can actually have the Wolfram engine as a library, and you can take it and set it up so that the Wolfram engine is actually linked in to your program, so you can create a program to distribute that will simply call an API that is actually part of your program that makes use of the Wolfram language. So the Wolfram language it's a very general thing, and we're trying to make a whole collection of products that make use of it, that sort of support different kinds of workflows. So the first one that came out a couple of months ago is our programming cloud, and kind of the concept here is it's all about creating code and deploying it in the cloud, on the web, and so on. And kind of getting one in the shortest possible time, sort of having the minimum algorithmic startup, so to speak, going from sort of the algorithmic idea through all the kind of knowledge that we have in the Wolfram language to something which is deployed in the cloud and actually running in the shortest possible time. And and as I say, the cloud, it can either be our public cloud or it can be a private kind of corporate cloud. Well, another platform that we have, which is coming soon, is there we go. We call the Discovery Platform. This is something which is kind of a step up from Mathematica. Mathematica is very widely used by R&D folk around the world. The Discovery Platform is kind of the full Wolfram Language version of the kinds of things that people do with Mathematica, the notion is to be able to get sort of unlimited access to all sorts of data and knowledge, to be able to make progress in R&D and to kind of use the methodologies that we've been able to use for years in doing that. Well, another thing that we are doing is one of the interesting things with the Wolfram language is we now have a language which is sort of simple enough to write and read that sort of it can be done by anybody, from kind of the most sophisticated kind of professionals down to kids who are learning their first programming language. And one of the things that's been interesting is we've been sort of studying using the Wolfram language as a first programming language because it's a language where you don't have to type very much, lots happens, and it's easy to look at code and understand roughly what it does. It's kind of a different model of learning programming languages that's more analogous to the way people learn human languages. It's sort of an immersion language learning methodology that seems to work, where you have a small set of principles, which are sort of the grammar of the language, which you learn after you've been immersed in actual code that works and been given sort of the opportunity to explore code on your own. So, for example, we have a thing we call Programming Lab, which will be coming out soon, which is a system aimed at kids that uses the Wolfram language to basically explore programming kind of from the very beginning. So that's that was a sort of an unexpected application of building sort of an extremely high-level programming language, is we sort of automated enough that it becomes accessible to kids and so on, and very engaging, and something where one can sort of teach computational thinking not just in the context of computer science, but in the context of any other kind of class, whether it's a geography class or a history class or something like that. We've got all sorts of knowledge that in the system that immediately lets you do computational thinking in those kinds of contexts. Well, so in terms of things that we're building from the Wolfram language, another big one is our data science platform. This is something which is optimized for kind of the data science workflow. And sort of the basic concept is data comes in from somewhere, analysis happens using all of these things that we have in the Wolfram language, and then reports get generated at the end. And this whole workflow is something that at this point we can do in a very nice, clean way. Let me try to show you. Let's try and show you this. So I should be able to show you. Here we go. Okay, so what this is going to do is you can set up new data, you can upload data files, you can connect to external data sources and so on, and we can then go. Let's see what I've got here. Okay, so then this will be a typical kind of template, I hope, that one might build in the data science platform. Let's see what this is. Okay, so this is a template that has to do with tracking my personal email inbox, and it's looking at the number of unread messages that I have and so on in my inbox. And now we can go ahead and say deploy this as an automated report. So we have all kinds of options here, but I think if I go ahead and say create a report here, create a report, it will go and go off and try and start creating a report. Now I can tell it to go, and usually it would have a schedule to generate the report. I can say run the report now, and it will go off, and I hope, let's see, where do I go to find the report? See what happens here. Here we go. Okay, so here's the results of running that report, and this is so grim. That's my pending email queue for the past year, with a few good periods. Look at that. So this is kind of an example of our data science platform, and again, the concept is data comes in, analytics happens in the middle. I could probably run a bunch of machine learning and time series analysis on my email queue and discover some things I might or might not like to know. And then at the end, reports are generated either on a schedule, sent by email, alerts are generated, all these kinds of things. So this is kind of the concept of our data science platform that will be coming out shortly. And by the way, all these reports are CDF documents, so they can all be interactive too, and you can have dynamic kinds of things going on within these reports. Well, okay, let me talk a little bit more technically about what's going on inside the data science platform. One of the important elements there is, let's see if we can get this to work here. One of the important elements is a thing we call Semantic Import. So this is making use of our natural language understanding stack to take typical use is fairly structured data, but data that is structured but not yet semantic. So here I'll just go and read some data off the web, and hopefully I'll be able to, I don't know how big this data is, and what will be happening is semantic import, oh, that's a bad sign. Who knows? I'll try it one more time. That's it? You think I should quit? All right, I'll retry this. All right. So anyway, what it should be doing is taking some lump of data off the sort of raw web and going ahead and trying to use our natural language understanding stack to read in that data and to notice that, okay, there are a bunch of, within that data, which is just plain text, there are a bunch of states that it can recognize as actual entities that are understood by the Wolfram language and so on. And now, okay, so there are 15,000 entries there. So now we can go ahead and let's do an actual computation. I had one here that is now going and making use of some kind of data manipulation and analysis. Let's see what this does. This should be munging that data and producing something interesting from it. So I think this is, I don't know what this is, some kind of income inequality data. So we can go ahead and just be doing this, and now from that raw data from the web, we were able to turn it into something meaningful and then able to start doing analytics on it. So this is kind of the first step in the pipeline for the data science platform. You don't need to turn your data into something semantic, but you can turn your data into something semantic. This semantic import was happening all locally. If I gave it some slightly different options and so on, it would be using the whole natural language understanding stack and ontology that we have within Wolfram Alpha to understand the data that I was feeding in. In fact, we have a thing that's coming soon called the Semantics server, which is a system that makes use of our whole semantic stack as a service that can be applied inside other programs and so on. Well, one of the things that we've done here is, one of the questions is, okay, you've got this data, how should you represent it in the system? And you know, there's SQL and there's no SQL and there's hierarchical databases and relational databases and so on. One thing that we've done is to make use of kind of the symbolic language ideas of the Wolfram language to come up with something which is kind of a modern symbolic melding of kind of the relational and hierarchical database ideas. So here's an example. This is a simple data set of planets and their moons. And so now we can go ahead and start doing things here, and we can see, let's say we want all planets and we want the radius of all the planets. Okay, there we go. That's easy. Then we can say, let's say we want all planets, we want their moons, we want the length of the sequence of moons, of the list of moons. So that will tell us how many moons each planet has, and maybe we can go ahead and take that result and make a pie chart and show that you know, which planet is the winning one in terms of number of moons. Or we could do something a little bit more sophisticated where we're starting to make use of more of the symbolic character of the language. We're saying take planets and their moons and look at the moon that's maximal by the key mass. Or we could go ahead and say, same kind of thing, we could then apply another function here that just extracts the keys, and we'll find the most massive moon for each planet and so on. Or we could go ahead and say, let's take something a little bit more complicated. Let's take all the planets, all their moons, and now we're going to just feed that into something which is finding the quantity, the radius of each planet, and then making this little piece of graphics. And so now we've got some little infographic of the moons of various planets in order and their sizes and so on. So the concept here is we're making use of sort of the power of symbolic programming that we have in the Wolfram language to create this kind of new way of thinking about databases that can be manipulated symbolically. Okay, well, so within this data set system, we actually have a whole hierarchy of different ways to work with data. And as we do throughout the Wolfram language and throughout our technology stack, we try to automate things as much as possible so that the user doesn't have to really think about what the kind of the mechanics going on underneath are. So sort of at the first level, one's just manipulating data in memory and just doing computations where everything is stored in memory. There's a second level where one's dealing with files. There's a third level where one's dealing with existing databases. A fourth level where one's dealing with distributed databases. We're gradually sort of climbing up these successive levels to be able to manipulate larger and larger kinds of data using the exact same language and code and mechanisms that we have for much smaller data. So you'll be able to use the data science platform with the exact same kind of programming for all these different sizes of data. Well, there's a whole elaborate framework of dealing with data that exists that we built for Wolfram Alpha that involves not only sort of the underlying querying of data in all sorts of ways, but also the ability to use natural language to ask questions about data. And it's sort of been an interesting competition in the development of Wolfram Alpha. We've got sort of underlying querying technology for our data and databases and so on, and we've got linguistic understanding technology, and every so often one of them gets ahead of the other. So sometimes we can understand more queries than we can actually compute with. Sometimes we can compute with more queries than we can understand. But we're gradually trying to sort of move both of these things up, and we're trying to set it up so that this kind of natural language querying mechanism is also available directly within the Wolfram language. I should say that the Wolfram language has plenty of ability to deal with natural language right now. So for example, one typical thing is we have these things we call interpreters, and this is again using the natural language understanding stack that we have. We say interpret as a city the string NYC. This is how these smart fields that I was showing before in our forms work. We could say interpret as a semantic number TWO space thirds, and it will go ahead and interpret this, I hope. This should be instantaneous. What's it doing? Scary. Okay, try it again. Who knows? There are lots and lots of different domains of, let's see, we've got, we could say, we could ask it, what different types of interpreters do you know about? And there's hundreds of different kinds of interpreters. So for example, we could say, let's give it, let's say we're expecting a disease and the actual string we're given is heart attack. It will then canonicalize that to some standard thing that's represented. I think this is an ICD-9 code here. So we can. So this is a way of building our. This is how we start to build natural language capabilities into the system, and in fact, we have a much more sophisticated version of this that's coming soon, where one can define one's own grammars and then make use of, as elements of those grammars, make use of things that are built into the natural language understanding stack that we already have. So for example, this would deploy a very simple grammar that is for setting an alarm clock. So it has a very simple piece of linguistics for setting the alarm clock, and then it has a grammar token here that says expect a semantic time that will make use of the whole standard natural language understanding stack. So this is a way that I think people will end up building lots of kinds of natural language querying methods for databases, lots of ways to control devices using natural language, and so on, making use of our existing natural language understanding stack. So, for instance, let's see if I can pick one up here. So this is a fairly elaborate example. This is using the GDELT database, connecting to Google BigQuery database, and then using a slightly more elaborate grammar here, and then just pulling in data. And so now it has, says this database is a database of news, and so this has a map of ceasefire violations in 2014, apparently, based on that natural language data set. And this is all happening where there's the actual query here is a natural language query that the grammar for that natural language query is defined here, leveraging the natural language understanding stack. Then that grammar, that query is turned into something computable, which is going off and calling this the API, doing these queries in the back end to then eventually generate this geo map there. Well, so this is one of the things we're doing. One thing that's interesting, when let's say you generate a report. Somehow, you use natural language, you use the Wolfram language, you use the data science platform, you generate a report. And you've got that report, you generate a report, you generate graphics, you embed that graphic somewhere on the web, something like this. The question is, where did that graphic come from? Usually when you see a graphic in some research report or some such other thing, it's just like, okay, there's a picture, that's nice, maybe you can read some text around it, maybe you can figure out from that text where the graphic comes from, how it was generated. Our idea is that whenever you have something like a graphic generated from our technology stack, there'll be what we call a compute back link. And so underneath there'll be a little thing that says source, you click that, and you'll be able to see, depends on how the author set it up, exactly how much you can see, but you'll in principle be able to see the Wolfram language notebook, as we call them, that generated that graphic. So you can start going back and saying, okay, here's a picture, now what generated this? Well, what generated this was this piece of code here. That piece of code is making use of data here. That data is again accessible directly through the technology stack. So kind of the notion is that you don't just have dead pictures in your reports and so on. You instead have things where you can go back and see how they were computed, and you can make use of the underlying data and so on. I think in time this is going to be what people expect. They want something where they can actually build on the material that's in the report. I should say that if the report is done with CDF, for example, the actual report itself can be interactive, and you can again use this compute back link mechanism to go and see where all that code came from and so on. I think in research, sort of the idea is, is it a data-backed publication, or is it just some dead publication that doesn't have sort of data backing it up? Well, so when you have this data, where do you store it? Well, you can store it in our cloud, one of the things we'll be doing is building a sort of global data repository using our cloud that can make lumps of data available, sort of published data globally. We can do very interesting things with data in our technology stack, in our cloud. For example, we can use our whole semantic import mechanism to be able to make that data semantic, to be able to understand the meaning of the data, to make the data computable. We can it's absolutely routine for us to be doing visualizations and analysis and so on that data. That's all stuff that for us is kind of for free once we have a data repository with data in it. So one of the things I should mention is when we think about making data semantic, we have something that we call WDF, that is something that more will be emerging about in the next year or so. The idea of WDF, if we could only get to an actual base, okay, is, oh yeah, it even has a tagline that says it, take data and make it meaningful. The concept is to be able to make use of our ontology and semantic structures and so on, to take whatever data you have and represent it in a symbolic semantic way. And in a sense, you can think about this as taking everything we built for Wolfram Alpha and its ontology and kind of opening that up so that everybody can hang things off the ontology that we've built for Wolfram Alpha. And the great thing about the Wolfram Alpha ontology is we actually know it works because we have an actual big system that's running off all of this ontology. It's not some theoretical ontology that we made up. It's something that has actually been built based on real data and a real working system. So, and it's not a static ontology. It's an ontology that sort of has full sort of computability, and it maintains dynamic algorithmic relationships and so on. This is WDF is kind of the representation that we'll be using for our data repository. It's also the representation that our data science platform works with. Another thing perhaps to mention is that so we make use a lot of UUIDs in dealing with data and dealing with objects in our cloud and so on. UUIDs are important because you generate a UUID and you can be guaranteed that it's going to be unique wherever you generate it from. So if you have private clouds and private data repositories, for example, you can be representing entities in those data repositories with UUIDs, and you're guaranteed that those entities will not collide with each other. And generically, data sets that we'll be dealing with will just be represented by UUIDs. But some of the data sets will be data sets that we want to curate and give names to and so on. And one of the projects that we have now is curating named data sets. So what we have been doing in the past is taking data and making the data sort of every individual piece of the data computable. Sort of the idea now is to take whole data sets that are sort of named things that people know about and to set those up as kind of entities on their own and be able to make use of them. And hopefully, I think many people here, we've worked with data sets that you guys work with. I think there will be many data sets that it makes sense to put in sort of raw form as curated named data sets into our infrastructure. One of the things that, okay, so we're intending to do a lot of curation of data sets as entities, so to speak. Another thing that we are curating is APIs. There are lots of APIs in the world, and we're interested in setting things up so that it becomes easy for people to query APIs. Let me see if I can do this here. Let's try this. There we go. So when we come, so the notion is that we have a variety of APIs. Here are a few APIs that we're dealing with here that are different kinds of services. And the idea is that we can connect to one of these services. Here we're connecting to Open Library. Okay, we just opened a connection to Open Library. Now we can do a search in Open Library. And what we're doing here is we're having a fairly raw, okay, so I just searched for myself as an author in Open Library, and it came up with a bunch of books there. Maybe I can do a search for a particular book and try and pull up a cover of a particular book. I wonder where that particular cover comes from. Okay, we can't tell. But the notion here is that we're curating APIs so that within our system you can get easy access to a whole variety of different APIs. In the past, we've curated data formats, for example, so there are probably 500 different data formats that we can import and export from within the Wolfram language. We're now doing the same kind of thing with APIs. And kind of our approach is to go on two paths. We're having what we call connected services, which are APIs, where it's a question of having the ability to connect, but we're not kind of dealing with all of the authentication issues with that API. You may need to have sort of separate authentication with that API. I mean, we're supporting OAuth and things within the Wolfram language, but you may need to have sort of a separate key that you arranged with whatever the vendor of the API is. So that's the first step, is kind of connected services. The second step is what we call integrated services, where we are dealing with the interaction with the API vendor, and where the notion is that we're using our cloud infrastructure and the billing mechanisms and so on in our cloud infrastructure to let people just use those APIs as integrated services within our language with separate sort of arrangements on the back end with the vendors of those APIs. I think that in both of these models, it's a pretty interesting way for lots of kinds of organizations to expose their data because we have this whole kind of infrastructure for taking data and letting people compute with it, whether it's directly within the Wolfram language or in apps that people build on the basis of the Wolfram language and so on. Okay, so and one of the things that sort of has opened up a lot for us in this area is the fact that we now have a whole micropayment mechanism through our cloud infrastructure that makes it possible for us to interface with other kinds of APIs and so on. Okay, final thing I want to talk about is another kind of source of data, which is the Internet of Things and connected devices. So we're keen to make use of the Wolfram language as sort of a high-level language for the Internet of Things. And it's very important for that purpose that the Wolfram language has sort of built-in data semantics, as well as a lot of existing built-in data. So when we deal with connected devices, one mechanism that we have for dealing with them is absolutely directly. Within the Wolfram language, there's a framework for just actually connecting to a device. So you can say, you know, device read time series, and you can connect to a device, and you can start reading a time series of data from that device. That's a device that you actually plug in with a wire to your computer. So there's a whole mechanism for dealing with that and for handling, for example, the time series of data that come from such devices. The other thing that happens in the modern world is that one has some devices that are somehow connected to computers through some wireless connection or through the web or something like that. One of the things that we did, because we're into curating things, we decided, I was curious, just what are the various connected devices that are out there in the world? And so I thought, let's just curate all the connected devices that are out there in the world. So far, there are 3,682 in our list. And this is a big, long collection of all sorts of different kinds of connected devices that measure all sorts of different kinds of things. I mean, if we say, what kinds of measured quantities do these measure? You know, some are measuring radiation dose, some are measuring illuminance, you know, body mass index, and so on. Each a different set of devices. Of course, all this data is we've made computable, and it's in Wolfram Alpha, and so on. Well, for any one of these devices, there's what one might call sort of the first mile problem. How do you go from the device, the scale that's sitting on the floor or something, to the cloud? Okay? And there's a whole sort of messy area that's going on right now of how you sort of solve that first mile problem. But let's assume that that problem has been solved. Then our goal is to take whatever can be fed into the cloud and be able to build a pipeline for doing analytics and making the data that's coming from that connected device as useful as possible. Whether it's producing a dashboard or making an API or synthesizing measurements across lots of devices and so on. So we're making sort of a general device analytics platform that's primarily intended for device manufacturers so that they can just concentrate on building their device, and then it's up to us to handle the whole cloud analytics infrastructure and so on aspects of this. Well, there's an important element that we're building to support that kind of activity, something that's not out yet, but it's something we call our data drop. And the concept of our data drop is it's a universal data accumulator for, as it says, devices, sensors, programs, humans, and more. And so the notion of the data drop is you accumulate data from anywhere. It's got a web API, you can send it email, you can embed code in Java that pushes things to the data drop, you can tweet to it, you can get data in from an Arduino, you can do all kinds of different things. But the notion is you're getting data into the data drop. So I can show you a little bit about how that works. So let's go and so obviously one way you can get data into the data drop. Let's kill this off. We don't need that anymore. One way you can get data into the data drop, of course, is using the Wolfram language. So we can say create a bin here. This is creating a data bin. Great. Let's connect here. Hopefully this will connect. That is a very bad sign. Let me see whether anything is alive here. You think so? That's the Tally's universal answer for what to do when things go wrong. Let's try it again. That must be the key to our R&D effort. Let's see if this works. Ah, it did work. Okay. Okay, so what we did here is we created a data bin. Okay, and it has a certain ID, and it has various other characteristics. And now we can go and take that bin, and we can say, okay, let's add, and the data that we're going to add to the data bin is just there's this variable now that just gives us the current time. So we go ahead and say, we can add that to the data bin again. We could, write a loop that just says do that 3 times or something. Just go ahead and just keep adding. And every time you'll see it's adding entries to this data bin. And now we can go ahead and say, if we want to, we can say, okay, what values are there in the data bin? And there we'll see the things that we pushed into this data bin. And now we can go ahead and say, we can do all kinds of computations with this. I mean, if we wanted to, I don't know whether I want to tempt fate here. I can probably try, let me see if I can do this. Let's try just, let us try taking this data bin. Where is it? There's the name of the data bin. Oops. And let me just try, I wonder, that little line sent with postbox looks a little weird, but let's just try sending in, sending some, are you sure you're ready to send this message? Why wouldn't I be ready to send this message? Maybe I should take off those, I don't know whether that's important, but okay. That was actually what I had back there was those were some, that was mail from the data science platform telling me that the report that I told it to generate ages ago was actually generated when I told it to generate it. But now what I should have here, hopefully, is, maybe not. I should have been able to add that data to the data bin. Let's see if that worked. No, it didn't. The mail has gone astray somewhere. But the idea, anyway, if I had actually typed the right things in, is that you can feed stuff to the data bin, to the data drop in lots of easy ways. So here's an example. This is a data bin that was created. This is a data bin that's based on a sensor that's sitting in a refrigerator in a break room at our company. Okay? And the sensor is measuring temperature and light. And so I think if we can go ahead, and it's been just collecting data, it's got 2,300 data points, and we could go ahead and say, let's go get the data associated with this data bin, and let's see whether we can, let's see whether it connects to this thing and so on. So this is going to our cloud and reading, I hope, should be instantaneous. This is a very strange, oh, well, it did something, okay. So now we can say, for example, let's make let's take that data. It's got 2 event series here. And so this is, for example, the temperature event series for the refrigerator. And I guess that's every time the door of the refrigerator was opened, there's a temperature spike and so on. We could go ahead and say, let's take the, let's make a histogram of the temperatures of the refrigerator over this period of time. And we should see a result there. Or we could do all kinds of things from this. But what's interesting here is this is just some little sensor, and all it knows is a web address, and it's just pushing data to that web address. And then within our stack, we're able to access that data. And by the way, if I type this data bin ID into Wolfram Alpha, we will soon be able to also generate a report directly within Wolfram Alpha and downstream within all the intelligent assistants that are based on Wolfram Alpha and so on, so that you can just push data into our data drop, and then you can go ask Siri or whatever else something about that data, and it will be able to give you a report on that data. Well, lots of it'll be, for low-frequency data, it will be free for people to just push data into our data drop. You'll also be able to arrange to get high-frequency data pushed into the data drop, and to get private clouds and so on that can store versions of our data drop, all kinds of elaborate things like that. I think one of the things to realize about data that's going from connected devices is we're interested in having processing be able to happen with our language in lots of different places. So in this case, the data drop is taking data from a potentially quite dumb device, pushing it into our cloud, and then we're doing computations on the data in the cloud. Another possibility is that the device itself is smart enough to be able to run our language. And I mentioned that we're developing versions of the language for various embedded processors. There will be a variety of versions of that. Already, since the end of last year, our language has been bundled on the Raspberry Pi, little tiny $25 Linux machine. That's a place where one can sort of take the processing and put it inside the device. So one's having sort of Wolfram language code that can run doing sort of pre-processing on data, taking an image and doing first pre-processing on it right within the device, or you can make the decision to move the data to the cloud and do the processing there. And it becomes a purely sort of tactical decision whether you have the processing done on the device or in the cloud. Well, there are lots of applications of all this kind of thing. There's a whole sort of personal analytics adventure. Some of you may know I've been a data enthusiast for a long time, so I've collected huge amounts of data on myself for 25 years or so. That's my trace of email as a function of time, lots and lots of data. But this is something that will become easier and easier for people to do, and feed it from connected devices through our data drop into the cloud and actually get computations done. We've also, as some of you may know, we've worked a lot on things like Facebook data. This is data that we got based on the personal analytics that we provide within Wolfram Alpha. You can connect Wolfram Alpha to your, oh, maybe not. You can connect Wolfram Alpha to Facebook, and you can have it do an analysis of the data that Facebook has about you based on the Facebook API. And from a large number of people doing that analysis and a fair number of people checking the box to become data donors for us, and for another set of people allowing us to use anonymized data from them, we were able to do this very large study of kind of the world according to Facebook, so to speak. And that's sort of a typical type of thing that's, again, possible through kind of the whole pipeline of data analytics that we've been building. So I might mention, we're talking about devices and so on. There's a question of when you have different kinds of devices, how many different kinds of things could you in principle measure? Well, this is something that we actually know because we've curated this for Wolfram Alpha. There are about 10,000 kinds of things that people measure that you find in the literature, whether it's dynamic viscosity, or whether it's one that really confused me was moles per acre, which is actually the number of it's a thing in agriculture where it actually involves actual moles aerating the soil, and it's a certain number per acre. Anyway, so that's one of the 10,000 different kinds of things that people measure. So one question is to sort of curate all those different kinds of measurement, and then the question is what kinds of devices do you need to do all those kinds of measurements? And one of the things that we've realized from curating these different kinds of measurements and so on is that there's actually a whole sort of global measurement graph that says, okay, so for example, you can say, this is actually not yet available in Wolfram Alpha, but will be soon, devices that measure dynamic viscosity, and it knows the various different kinds of devices that measure dynamic viscosity, and it knows the ranges of measurements, and so on, and so on, and so on. So one question is, if you're going to if you're going to try and measure 10,000 different kinds of things, do you need 10,000 different kinds of sensors to do that? And the answer is absolutely not. What you can do is take all those different kinds of measurements, and you can say, what are the fundamental primitives that you can build up those measurements from? So, for example, there are some broad spectrum sensors, like a camera is a good sort of broad spectrum sensor, because with a camera, when you get data from a camera, you can process that data to figure out all kinds of things. Like you can have a camera just look at you, and it can see that your skin is getting redder and less red as for every heartbeat. And so just by taking an image and processing that image, you can deduce heart rate. So similarly, there are many different kinds of things that you can deduce. Of those 10,000 different kinds of things you can measure, you can start building up this graph of from what can you deduce what. And so we've been interested in kind of thinking about what would it take to make sort of a universal sensor platform that has a small number of kind of broad spectrum sensors. It might be a mass spectrometer, it might be some chemical sensor, it might be something that some hyperspectral imaging sensor, might be a bunch of different things that are sort of broad spectrum sensors, but a small number of them, maybe a dozen, less. But from those sensors, be able to just use science effectively to build up an actual way to measure each of those 10,000 different possible things that can be measured. So I've been interested in figuring this out, and I don't yet have a version of this universal sensor platform, but it's sort of a direction that we've been going in. And sort of our notion is to build kind of the data operating system that goes above this universal sensor platform. So underneath universal sensor platform, it's measuring stuff, but what you say is, I want to measure quantity X. I want to measure wind speed. And somehow underneath, some measurements will be made by this universal sensor platform, and then our sort of data operating system layer will figure out the actual thing that you want to compute. So, okay, so there's kind of this is sort of a direction that we're going for. It's kind of under with the Internet of Things, instead of having 5,000 different kinds of devices, have a universal sensor platform that purely in software can be made to measure different types of things. There's sort of a lot of different kinds of data that one can deal with. I'll mention, okay, two last examples. So I suppose a sort of meta theme of this conference is there's lots of very fascinating data out there in the world. There's many more things in the world that you can measure and get data about than you might possibly imagine. I'll just mention two areas that we're going into, which are sort of examples of new types of curation and new types of data work that we're dealing with. So one type of data work has to do with machines and devices and systems. So for example, we have already built in, I hope, let's see if this comes back, data about all sorts of physical systems. So this is about a harmonic oscillator, and we know all kinds of elaborate wave functions for harmonic oscillators and who knows what else. But one of the things we want to do is there are many different kinds of machines in the world, and we actually have a product called System Modeler, which is aimed at the systems engineering market, where people represent all sorts of elaborate and complicated machines using a language called Modelica, which is sort of a standard language for representing engineering systems. And the idea is that you can represent all those different kinds of machines, whether it's a machine that is some sort of abstract kind of machine that you made up, or whether it's a machine that some particular vendor sells. All of these things can be represented symbolically in this Modelica language. We can take a representation of a machine, so there's a particular machine, and now what we're doing here is simulating, so this machine, it's a rectifier, we're now simulating that rectifier, and now we can go ahead and take the results of that. This is being done right now by linking our system modeler product into the Wolfram language. But what we're aiming towards is really integrating all of this capability for dealing with machines and systems directly into the Wolfram language. So the notion there is that we are we've curated many kinds of things. We've curated, cities in the world. We've curated kinds of chemicals. We've curated lyrics of songs and things. We've curated kinds of connected devices. Yet another kind of thing to curate is machines and their operation. But one thing that's interesting about that curation is it's very algorithmic curation, in the sense that the thing you're curating is the algorithm that describes the operation of the machine. And so the idea is to do that for all common kinds of machines, all kinds of things that you can buy from different vendors and so on, and then to be able to take those curated representations of machines and be able to compute with them directly in the Wolfram language. So that's kind of another type of curation. Final type of curation that we've been interested in is kind of a lot of what we've been interested for a long time in math. That's why we have a product called Mathematica, for example. One of the things that's true in math is there's been a lot of work done in math over the last many centuries. About 100 million pages have been written in the literature of mathematics, and they contain about 5 million theorems. And so one of the things that we think is worth doing is just curate all the published theorems of mathematics. Why is that interesting? It's interesting because if you describe kind of a pure mathematical construct, one of the things that is of great interest is to say, well, what theorems that people wrote down over the past 3 centuries apply to this mathematical construct that I'm thinking about today? So we've had a project, actually this is a project that was, unfortunately, unlike many of the things that we curate that have terrific sort of commercial application, curating all the theorems of mathematics is really a philanthropic effort. We have some support from the Sloan Foundation, for example, for doing a sort of corner of the curation of the theorems of mathematics. We worked particularly on ones about continued fractions, and we've curated some fraction of all the known theorems about those. It's sort of interesting to see what does it look like underneath. What we need is some kind of representation of, just like we have representations in our language for networks, or representations for cities, representations for other kinds of things. We also need representations for all of the concepts of pure mathematics. We have many of the concepts of mathematics that have been applied in serious ways. We already have from Mathematica within the Wolfram language, but we need to go on and sort of have a representation for all the different kinds of concepts that have come up in sort of those 100 million pages of literature of pure mathematics. So this is a challenge for the future, and we've just been sort of trying to mobilize the world mathematics community to help with this challenge, and I think it's going to go fairly well. Within our language to date, we have about 5,000 different kinds of different functions, different constructs. Pure mathematics is actually a big chunk of additional sets of constructs, probably many hundreds, possibly 1,000 more concepts that have to be added to the language, but it's something that we're working towards. So it's, and one of the things that we're doing, whether it's dealing with machines or mathematical theorems, one of the things that we've sort of learned is that one of the, from a sort of our understanding of data and our understanding of knowledge and knowledge-based systems and so on, we've sort of developed a design methodology which allows us to take each successive area and attack it and sort of bring it into our kind of computable knowledge kind of framework. And so I think this is something that we've been doing for many years, and every few years we get even more ambitious about the kinds of areas to which we can apply this sort of methodology. So so if you'd asked me a few years ago this sort of computational knowledge idea, to what can it be applied, I would have described to you some set of things. As we understand more about what's possible, and as we build out sort of a bigger technology stack, the set of things that we can apply this kind of computational knowledge methodology to expands. And I hope one of the things that we're keen on is to be able to take data that people, organizations have collected over the course, in many cases, of many decades, and be able to provide really the best possible framework for taking that data and making it as useful as possible, making it so that one can get as many sort of answers from that data as it supports, and sort of compute with it in the best possible way. And I should stop there, and I'm sure I went over time, and I'm sorry. So thanks very much.